From the Way Happy Studios, this is Mr. Meyer, and we are coming from the South Studios today. We hope you are having a great day, and we are talking about anti-differentiation. So as you know, if you were to learn something in mathematics, usually we will show you how to do one thing, and then we'll show you how to undo that thing, because that's what we care about. How do you undo something you did? You learn to add, and then you learn to subtract. You learn to multiply, then you learn to divide, and those are inverse operations. And then you learned squaring, and then you use square rooting, and then in trig you learned sine, and then you learned arc sine. So everything was always undoing itself. Well, guess what? In calculus we have the same thing. We have derivatives, which talk about gradients, and then or slopes, and then tangent lines on that. And then we have integration, which is, hey, look, somebody shows you an equation that is a derivative, and could you get me back to the original equation? So kind of undoing what you have done. So here we go. The first example I want to set you off at here is this example one here, right here. And it says, look, the derivative, so they're giving you an equation. They're saying the derivative, and what does that mean if we kind of look at it? That means somebody took the derivative of y with respect to the variable x. So x is what they took, all the x's is what they took the derivatives of, or used techniques to take the derivative of. And when they did that, they got 2x. So what do you think the equation would be? Well, you guys know the power rule, right? So you have like 3x to the third, then you know that you would take the derivative, you'd bring the 3 out in front, and you'd get 9x, and then you'd power down by 1. So we kind of want to undo that. We want to go the other way. So what could they have done? Well, I know I would have to power up. It would have been had to have been x squared. So could y have been as simple as x squared? Well, let's see. Do you take the derivative of that and you get 2x? Yeah, sweet, right? So that is the derivative, or that is the original problem. So there you just did what we call the antiderivative, or integration. We're going to have to come up with some tricks though, right? Like let's look at another one. Let's try this one, x to the half power, which is, so the derivative, this is the derivative of y with respect to x is given to you by the square root of x, or x to the half, whichever one you like. Probably going to like the power better, because then I can try to figure out what to do with it. Could also be written like this, by the way, integral of x, and then this dx says we took the derivative with respect to x. So it's just saying, hey, by the way, I took the derivative of the x in case there was more than one variable or something. So I go ahead and I look at that, and I got to try to figure out what this is. And anytime somebody gives you an equation that has a derivative in it, that's called a differential equation. Fancy class, you get to take it in college, and it talks about a lot of here's derivatives. You tell me what the equation was. All right, so go ahead and let's see what we're going to do. What the heck could they have done? Well, they had to power down, so I know it had to be x to the 3 halves, right? Because when they powered it down by 1, that's how they would have got the x to the half. And then they would have had to put the 3 halves out in front. So what would neutralize that would be, what, 2/3? So let's see. This is my guess, right? I'm thinking y prime, or y is this. I'm not sure. But what's cool about this is you guys can take the derivative, right? Bring the 3 halves out in front, and you would get 3 halves times 2/3, and then you would take the x and power it down by 1 and get x to the half. And lo and behold, I got it. So that is called integration, or anti-derivatives. And with that, you have completed section 1 of this chapter 17. Now we don't want to stop there. We want to move on. So I will give you this in class, and then we will move on. So let's try the next one. Constant of integration. Now that's kind of a funny thing, and I thought I wrote in here, but apparently I didn't. So let us talk real quick. I want to mention off to the side that could you tell me, oh yeah, I did, right here, review. I didn't see I wrote review. All right, review. Take the derivative of 5x squared minus 3. What do you think? 5x squared, let's see, we bring the 2 out in front, we multiply it by the 5x squared. Oh, no we don't, we multiply by the 5, really, and then the x, and we power it down by 1, and then the derivative of 3 is nothing, so it's 10x. There's your derivative, right? Well, let's do the next one. What about 5x squared plus 7? Alright, so let's see, we're taking the 2 out in front, multiply by the 5, we power the x down by 1, then the 7 gets nothing, that's 0, so it's 10x. Nice. All right, what about the next one? 5x squared, we're going to bring the 2 out in front and multiply that by the 5, power the x down by 1, and then 5/4, that's 0, so 10x. Feel like there's something going on here. All 3 problems were different, yet all 3 problems had the same derivative. That's weird. Huh. So that would be really confusing if someone were to do an antiderivative of 10x. If I said, hey, integrate 10x, right? You'd be like, okay, the integral is, let's see, I think if you'd have to go up, it would have been x squared, and the 2 would it'd be 5x squared, and that's what we did up, in section 1. But now we've learned that, oh no, there's this little thing, this constant on there that could have been there, and we wouldn't know it. So guess what? That's what your constant of integration is. You always, when you have to integrate, whenever you integrate, you put a plus c on the back end. Always plus c, saying, hey, look, there could have been some constant. There could have been 0. Or it could have been 5/4 for all I know. Could have been 5/4. It could have been 7. Could have been -3. I don't know. So there's some constant on there. And you have to always put that. That is the constant of integration. On the AP exam, that's a check. On the IB exam, that's going to be a mark. So be super careful. You always need to mention the constant of integration when you're integrating. So let's be a little more careful in this next section, right? If I have to integrate here, okay, so it was probably x to the 4th. And then, so they would have to bring the 4, so it probably have to be a half, right? Think it would have to be a half x to the 4th? Yeah, that looks good. Plus some constant that I'm not sure if it was there or not. Nice. And what about the next one? Let's see, go up a power. What would that be? 5 halves. So it's going to be x to the 5 halves. That means they would have to bring 5 halves out in front and make it a 4. Are you kidding me? They would have 5 halves times something. Let's call it m for Meyer. And it would have to equal 4. Now some kids can do this ahead. I'm going to have to do this on paper. I'll have 5m equals 8. And so m equals 8/5. So what did I do there? I just figured out that this was 8/5. Now how did I figure that out? Kind of just undid something, right? I knew that 2 things multiplied together had to equal 4. So what did I do? I divided 5 halves to the other side and figured out it was 8/5. So now look, if you take the derivative of this, you would bring the 5 halves out in front. The 5s would cancel, get 8 over 2, which is 4. X to the 3 halves. Oh, I forgot my constant of integration. Ho, ho, ho. There it is. So there is section 2. And you have now completed 2 sections of this chapter. Not so bad, right? I kind of think it's fun. All right, let's move on to section 3 then. Uh-oh, what'd I do? I hate when I do that. Section 3, which would make it way more fun. I can't even tell what that symbol is. There we go. It says, all right, are you noticing a pattern? I keep saying like I'm pretending like I'm going up a power and trying to figure out what I'm multiplying by, and maybe we should find a better way for this. So have you noticed a pattern for the power rule? There's a power rule for integration, right? And have you noticed one yet? I kind of feel like I have. And so I feel like I've been doing this right here where I went up to the 4th power, and then I had to figure out what the multiplier was. Or even here, I pretended really hard. We're going up to 5 halves, and then I did something. Well, let's see. If we always, for derivatives, we multiplied and then powered down. How about if you power up and then divide, right? And that's what you're supposed to say. That's what I was looking for you. If we were in class, I would say, I want you to say, well, in your own words, I would power up and divide. And divide. So come up with something to help you remember which way this is going. All right, so let's see. Key point 17.1, there it is. As long as your exponent isn't -1, and we'll talk about that later if it is, then here's the rule, right? You power it up, you divide it by that new power, and you add your constant of variation, or you're not your constant of variation, your constant, and you are golden. So that's the power rule, key point 17.1. 17.3, by the way, shows that you can just integrate things separately, which is kind of handy. So if you have the integration of 2 functions together, you can integrate them separately, which you probably know already and just didn't know. When I give you guys this equation and I say find the derivative, so I say what's the derivative of this with respect to the x's? Remember how you did them individually? You're like, oh, this is 6x and this is 2 and this is 0. So there's the derivative. Guess what? You can integrate those things individually too. I can integrate this, then I can integrate that, and I can tell you what the heck we have. So that's all that's saying. So here we go. And by the way, it's just me reminding you here, this doesn't work for when things are multiplied together or divided. There's different rules there. So this is just when you want to power up. So go ahead, let's try this trick. This example right here, I'm going to power up. So that's going to give me x to the -1. But then I'm going to divide by that new power, so I'm going to have 6 over negative 1. So what is that? That's negative 6 x to the negative 1, or maybe negative 6 over x. I don't know which one they're going to show or want, or multiple choice. I have to look. Free response, I'm good with either one. All right, so there it is. That's your new rule. Oh, what did I forget? I totally forgot something. Shame, shame. Plus c. That is embarrassing. That plus should probably be a little bigger. It shouldn't be just to the x there. All right. What about the next one? Oh, here's an example of doing ones, one each at a time. So we're going to go up to the third, and we're going to divide. So that's going to be 2/3 x cubed. I'm going to go up a power. So what's negative 2/3 plus 3/3? Is that 1/3? I'm going to go up a power. So x to the 1/3. And then I got to divide negative 3 by 1/3. So it's not like multiplying by 3. So it'll be negative 9, right? Negative 9x to the 1/3. And then the 4, I got to go up a power. So that's going to be up to 4 to the x. And divide by 1, so not a big deal. And then the plus c. Don't forget your plus c. Don't forget. All right, I'm feeling pretty good. You can pause at any time and move ahead, or just have some fun. And what about this one? What about when you have to simplify before you integrate? That could be a challenge too. Like, look, ooh, these are multiplied together. Ah, I'm stuck. I don't know what to do. I can hear the panic. Wait, stay calm. I can rewrite this as 3x cubed times x to the half. They have the same base. I can add their exponents. This is really 3x to the, what is that, 3.5? So you guys want to call that 6, 7 halves? Let's call that 7 halves. Let's integrate that, right? And a little note about integration is it should always have your integral symbol, and it should always have your d whatever. So be careful. Those two things come together. They're bookends of the problem, and they have to be there forever, forever, forever. All right. Cool thing I'll tell you later too is that 3 can go out front, and you can kind of ignore it till the end. It's a writer. It doesn't need to be there. It's just something that multiplied that x to the 7 halves. But I'm not going to do that yet. I'll do that later. All right. So let's see. We go up a power. So we're going to have to add 2 tooths to it. So it's going to be 9 tooths. So it's going to go up to the 9 tooths, and then I'm going to divide by 9 tooths, or multiply by 2 ninths. So if I multiply 3 times 2 ninths, I'm going to get 6 ninths, which most people would call 2/3. All right, I'm going to call that 2/3 plus a c. So there she is, right? That is the gorgeous work of me integrating. And last but not, and by the way, the cool thing about these things is you could always take the derivative to see if you're right, right? Just in case the back of your mind, you're like, I'm not sure I'm right. So you take 2/3 x to the 9 halves, right? And you'd be like, all right, I'm going to pull the 9 halves out in front. And I'm going to power this down by 1, so that'll give me 7 halves, which if I do this and this, that's going to give me a 3. These are going to cancel. I'm going to have 3x to the 7 halves, which is the same thing as 3x to the 6 halves times x to the half, which is what we had way back when, right? 3x cubed times the square root of x. So I can pat myself on the back and feel super good that I got it right. That's the cool thing about knowing how to undo something. All right, last but not least, oh my goodness, what is that? Well, ideas. I could foil the top. All right, I can foil the top. Like it. X squared plus 2x plus 1. And then I write this is x to the 1/3. Oh my goodness. Now we can break it apart as 3 little fractions, can't we? We call this x squared over x to the 1/3, since there's only one thing on the bottom here. It's really nice. 2x, x to the 1/3, and 1, x to the 1/3. And then now I could probably, a lot of people like to put parentheses around this. It says all of that is the derivative, which it is. So I'll make that pretty. All right, so now what am I integrating? Well, remember what you do with these, same base, you subtract the exponents. So you got, what is that, 6/3 minus a third is x to the 5/3. Then I got 2 over here, and I got x to the, what is that, 3/3. 2x to the 2/3, and then here I have x to the negative 1/3, and our 15 minutes are just about up, so we're going to have to fly through this one, kids. Hold on to your hats. Here we go. Up a power. So up 3/3 would be 8/3, and divided by 8/3 or multiply by 3/8. And then this one I would have to go up to 5/3, and I would multiply by 3/5, so it was at 6/5. And last but no, and that's not last but not least, this one I'd have to go up a power, so that'd be x to the 2/3. I would have to multiply by 3 halves, and last but not least, add a constant, and there she is, and we did it.